So the fifth video in this unit is on natural logs and base E, and I've alluded to these in earlier videos and also in class. We had the common log that was base 10. This is going to be the natural log, which is base E. And I have also shown what it looks like, what the graph looks like right here. Once again, you have the exponential graph with E as the base, and then you have the logarithmic graph that is its inverse. So natural log is just base E, so you can see across the line y equals x. And so there are several things to do here. I don't know why this is gargantuanly bigger than the rest of the objectives, but we are going to solve some exponential equations, and we're going to be doing all these other things as well. So these are a lot of words, but what I wanted you to take away from this is, why on earth do we even have logs? And until we had calculators, we needed logarithms to manage large numbers and very large roots. So for instance, you wanted to take the fifth root of something, it would be very, very difficult to do without a calculator. And so they developed these techniques of logarithms, remember that a log is equal to an exponent, to make those calculations easier. The exponential function is one of the most important of any of the functions that we use in mathematics, especially in the sciences, radioactive decay, bacteria growth, population growth, in financial, where we talk about continuous interest, loan payments, all of that is an exponential. They're also related to logs. They're the inverse of logs. So many times we evaluate an exponential using a logarithm and vice versa. Different bases. Base 10 is used by chemists. It says here on their measurements of pH and acidity of a liquid. Base 2 is used in computers. We call it binary. Base E, and I've written out what E is because, I've alluded to E a couple of times, but I haven't really told you what it is. It's a constant value, it's a repeating decimal value, just like pi. 2.71828 is the part I remember, and it's used in calculus and probably the most important base that we use. So we use logarithms to handle many of the computations in the sciences that would be very difficult otherwise. Okay, so the natural base functions are base E, and we learned on the previous screen that E is 2.71828. So E, or 2.71828 to the x, is used to model exponential growth. E to the negative x is used to model exponential decay. The inverse is the natural log, and it is just basically log to the base E. Log to the base E is abbreviated lnx, probably like log natural instead of log common, and so that's why it's ln. So to rewrite these in logarithmic form, we would start just like we did regular logs, and we would say log to the base E of 15 equals x. Remember this? E did it like that. So log to the base E is just natural log 15 equals x. So we don't have to write log base E. We can just say natural log. Same thing here, backwards arrow. So natural log of 23 equals x. Once again, the log is equal to an exponent. So we have natural log of x is equal to approximately 1.2528. We're going to write that in exponential form. So once again, we start with the base to the power equals here. So we have e to the 1.2528 is equal to x. All right, same thing here. E to the x equals 25. And that's really all, that's as hard as it gets right there. Okay, so here we are. We're going to solve base E equations. So the first thing that we want to do here is we want to get the e to the negative 2x by itself on one side. So I'm going to subtract 4 and divide by 3. So I've got 3e to the negative 2x equals 6. Divide by 3, divide by 3. E to the negative 2x equals 2. And I'm going to write that as a log, right? So I have the log base E of 2 equals negative 2x. And I'm going to divide both sides by -2. So I have the natural log of 2 divided by -2 equals x. And I'm reaching for my calculator because natural log has its own button. So the natural log of 2, closing the parentheses, divided by -2 is -0.346573. And that's how you solve that one. So once again, let's recap what we did. We subtracted the 4 to the other side, and then we divided by 3, getting e to the -2x by itself on one side. We converted it to a natural log and solved for the variable, knowing that natural log of 2 is just a number. It's just a number. So we can put it in a calculator and get a decimal. Okay, so here is a problem that we've already done. We're going to rewrite these as a single logarithm. Okay, so we note here that this is the power rule. So I'm going to write natural log of 3 to the 4th power plus the natural log of 6, right? This is the power rule. Then this with the plus is the product rule. So I'm going to write it as 1 log, natural log of 3 to the 4th power times 6. Now, that's going to be 81 times 6. What is that? We can do that in our head, can't we? 81, 6, 486. So the natural log of 486, if I did it right. We're working on mental math. I actually wrote it out, but there you go. All right, and a single logarithm here. So once again, you have the power rule going on here. And then you have the product rule for the rest. Okay? So I'm going to have the natural log of 3 to the 2nd times 4 times y. 3 to the 2nd is 9 times 4, so the natural log of 36y. All written as a single log. And if I wanted to convert that then to exponential, right, this would be e to the x is equal to 36y. Now, I don't know why you do that, but you still could. Okay, so finally, let's put this all together. We have 2 natural log of 5x equals 6. So the first thing I want to do is I want to divide everything through by 2 and have the natural log of 5x equals 3. Now, one thing we can do here, since this is the natural log, instead of logging both sides, we could exponential both sides. So we would go by the same base. So natural log is base e. So I would do e to the natural log of 5x equals e to the 3rd, and that's what this would look like. So what that does is it cancels because e and natural log are inverses of each other. They undo each other. So I'm left with 5x equals e to the 3rd. So I would have x equals e to the 3rd divided by 5. Now we're going to do tons and tons of these in class, but I wanted you to see that you can log both sides, you can do various techniques to solve these equations, and we will be doing these plus the inequalities in class. So I hope you took good notes. I hope you're practicing on your own because logarithms require lots of practice. And I will see you in class.